Humanity spent 50 years away from the moon, and the moment we decided to go back, everything changed. Welcome, I'm FactSpark. If you want more of this, hit subscribe. Let's get into it. Artemis II just launched. 4 real astronauts, 1 spacecraft, and a trajectory that will take them further from Earth than any human being has ever been. Not to land, not yet, but further. And that detail alone should make you ask, why now? Why go back at all? Because the answer is way bigger than you think. Let's start with what's actually happening on this mission. The crew will first do a couple of orbits around Earth, running system checks, making sure everything works before they commit to the big leap. Then they go. And they go hard, roughly 7,000 kilometers past the far side of the moon, far beyond its orbit, deeper into space than any person in human history. They won't land. They won't even enter lunar orbit. Instead, they'll follow what's called a free return trajectory, essentially using the moon's own gravity as a slingshot to bring them home without burning much fuel at all. 10 days total. Re-entry at roughly 40,000 kilometers per hour. Controlled, calculated, and absolutely insane when you think about it. This is Artemis II. But it didn't come out of nowhere. Back in late 2022, Artemis I did a similar loop around the moon. Except instead of humans, it carried 3 crash test dummies rigged with sensors to measure radiation, acceleration, and everything a real astronaut would experience. It was also the very first flight test of the rocket and spacecraft that will carry humans on all future missions. There were some issues with the heat shield during re-entry, but those seem to be sorted.
If things keep going well, Artemis III will actually land on the lunar surface, specifically the South Pole, sometime around 2028. So now the real question, and I genuinely want you to drop your answer in the comments. Do you think returning to the moon is worth the cost? Because after everything you're about to hear, your answer might surprise you. Here's the thing most people miss when this topic comes up. Going back to the moon is not just about planting a flag again. There's a political dimension, a scientific one, and an economic one, and they're all colliding at the same time. Let's start with politics, because pretending it isn't there would be naive. The first moon landing happened because the United States and the Soviet Union were locked in a space race. The Soviets had been winning, first satellite in orbit, first living creature in orbit, first human in orbit. America needed a moment that would define the era, and they got it with the Apollo 11 landing. That was the logic then. Today, the logic is similar, even without a Cold War. The space landscape has completely changed. It's no longer a 2-horse race. Countries from all over the world have sent missions to the moon, and even private companies are pulling it off. But the one moving fastest, the one that has genuinely shifted the balance, is China. Think about what they've done recently. They brought back lunar soil samples for the first time since the 1970s. They were the first nation to land a spacecraft on the far side of the moon, and they've announced plans to put Chinese astronauts on the lunar surface, potentially as early as 2030. That's not vague ambition. That's a concrete timeline.
So part of what's driving America back to the moon is exactly what drove them there the first time, the deep, uncomfortable fear of being second. That's not cynicism, that's just history repeating itself. And honestly, when competition pushes science forward this fast, maybe that's not the worst thing. But now let's talk about the part that actually keeps scientists up at night, in a good way. The far side of the moon is one of the most scientifically valuable pieces of real estate in the entire solar system. And here's why. Astronomers have been obsessing over a period called the Cosmic Dark Ages. This is an era in the very early universe, before the first stars and galaxies had formed, where the cosmos was essentially a dark, cooling fog of hydrogen gas. To study it, you need to detect extremely faint radio waves that were either emitted or absorbed by those ancient hydrogen clouds. Simple problem, you can't do that from Earth. Our own atmosphere blocks those wavelengths completely. The far side of the moon, though, it has no atmosphere. And because it permanently faces away from Earth, it's naturally shielded from all the radio noise we generate. Satellites, phones, broadcasts, all of it. It's the quietest radio environment humans have ever had access to. Projects are already being designed for this. One proposes stretching a wire mesh across a crater that's over 1,300 meters wide, with a dense metallic net in the center acting like a parabolic dish, focusing radio waves up to a receiver hovering above it, exactly like the giant radio telescopes on Earth, but built from lunar materials. Another project wants to deploy over 100,000 individual antenna strips, essentially aluminum ribbons, across an area larger than a major city.
The materials to build them, including the cables and solar panels, would be extracted directly from the lunar surface. Robotic fleets would do the construction. There's even a proposal to print the antennas onto inflatable mats that fold up for the journey and expand once deployed. From these observatories, we could look back at the universe's very first light. We could identify exoplanets with magnetic fields, one of the key factors that makes a planet potentially habitable. We could even scan for what scientists call technosignatures, patterns and signals from distant worlds that might hint at the existence of technological civilizations. You don't need to be a science fiction fan to find that a little extraordinary. And the possibilities don't stop at radio waves. Scientists have proposed telescope arrays on the moon that would operate in visible and ultraviolet light, reaching resolutions 100 times better than the James Webb Space Telescope. Imagine being able to image the actual surface of a star or resolve the disk of a planet orbiting another sun. There are proposals for gravitational wave detectors on the moon that would complement the ones on Earth. And even enormous infrared telescopes using a spinning liquid mirror to study the earliest structures in the universe. The moon, in short, is the world's best observatory, and we've barely used it. But here's where it gets even more interesting. Because all of that is about looking outward. What about looking at the moon itself? The moon has almost no erosion, no liquid water, barely any atmosphere, no recent volcanic activity, no tectonic plates grinding together. What that means is that large parts of the lunar surface are essentially frozen in time, billions of years old, largely unchanged since the moon itself formed. When we study those ancient regions, we're reading a geological record that Earth erased long ago. That gives us direct clues about how rocky planets form and evolve, not just the moon, but Venus, Mars, and Earth itself. We can study how the solar wind and cosmic rays have shaped surfaces over billions of years in ways that are impossible to observe at home. Then there's the South Pole specifically, and this is where things get genuinely exciting. In permanently shadowed craters near the poles, where sunlight never reaches, there is water ice. This isn't speculation, we've confirmed it. And that ice is scientifically priceless. It almost certainly arrived via comets and asteroids, carrying with it organic compounds and clues about how water and the building blocks of life were distributed across the early solar system. Studying it could tell us how life's ingredients ended up on Earth and help us assess whether similar conditions exist elsewhere. Which leads naturally to the question of actually staying. Because here's the part of this story that sounds like science fiction, but very much isn't. Both NASA and the Chinese Space Agency and the European Space Agency are actively planning permanent or semi-permanent lunar bases, not temporary camps, bases, the kind that could eventually support rotating human crews the way the International Space Station does today. Some plans go even further, towards something resembling actual colonies. Why would you want to live on the moon? Start with the basics. The moon is a testing ground. Its surface conditions, no breathable atmosphere, 1/6 of Earth's gravity, constant radiation bombardment, are genuinely hostile, and that makes them genuinely useful. Learning how the human body adapts to those conditions, developing the systems that keep people alive there, figuring out whether you can grow food outside of Earth's biosphere, all of that knowledge transfers directly to deeper space missions. The moon is the rehearsal. Now add the resource angle. The water ice in the South Pole craters isn't just historically interesting, it's strategically critical. You can drink it, you can split it into oxygen and hydrogen, giving you breathable air and rocket fuel, in situ, on the moon, for free. That changes the entire economics of space exploration, because the most expensive part of any space mission is lifting mass out of Earth's gravity well. If you can refuel at the moon instead of launching everything from Earth, you cut mission costs dramatically. The moon also sits on deposits of rare Earth elements, the materials that go into smartphones, electric motors, and basically every piece of modern technology. There's also helium-3, an isotope almost non-existent on Earth, deposited on the lunar surface continuously by the solar wind. If nuclear fusion energy ever becomes commercially viable, and it might, helium-3 could be one of the cleanest, most efficient fuels available. We're sitting on a potential energy reserve the size of a small world. And then there's location. Because of its much weaker gravity, 6 times less than Earth's, launching a spacecraft from the moon requires a fraction of the energy that launching from Earth does. If you build your interplanetary fuel depot there, if you assemble your deep space vehicles there, then Mars, and eventually everything beyond, becomes significantly more reachable. The moon isn't the destination. The moon is the launch pad. There are even proposals for harvesting solar energy from the moon's surface, where certain peaks near the poles are in almost continuous sunlight, and beaming that energy back to Earth via microwave or laser. Whether that ever becomes economical is genuinely uncertain, but it's being seriously studied. None of this is guaranteed. Some of these ideas will hit walls: technical, financial, political. Not everything being proposed will become reality, and the timelines keep shifting. The first crewed lunar landing under Artemis is currently scheduled for no earlier than 2028, and history suggests we should hold that date loosely. But step back and look at the full picture. You have a geopolitical race that's accelerating investment. You have scientific objectives, observing the early universe, studying planetary formation, searching for signatures of life across the cosmos that genuinely can't be achieved any other way. You have concrete plans for bases that would push human endurance and capability to new limits. And underneath all of it, you have the slow, serious logic of making humanity a multi-world species, with the moon as step one. Artemis II is not a repeat of the past. It's the opening move of something much larger. And unlike the last time humans left Earth's neighborhood, this time the plan isn't to come back, collect some rocks, and call it done. This time the idea is to stay. The second step was just taken. Where the next ones lead, that's the question the next decade will answer.
And trust me, you're gonna want to be paying attention. If this got you thinking, subscribe to FactSpark. There's a lot more where this came from.